Hello everyone. So we are going to continue our discussions of the chapter on mathematical preliminaries, and we're going to start a new topic today uh, called coordinate transformations. And the motivation for studying this topic can be directly linked to what we had discussed at the very first class of mathematical preliminaries. So let us quickly go back to that page, that first page, and uh, refer to uh, that motivation. So you see here that the same vector v was referred to a coordinate axis x1, x2, x3 in this particular form, and then alternatively the same vector v was represented in the x1 dash, x2 dash, x3 dash coordinate system through this system. What we want to find out in the current topic, that the topic that we're going to begin today, called coordinate transformations, is what is the connection, if any, between this representation and this representation. So with this motivation, let us begin our topic. Okay, so first let us draw a particular coordinate axis, a set of coordinate axes like this. So suppose we have these three coordinate axes, x1, x2, x3, and suppose we have another set of coordinate axes, let's say uh, x1 dash, x2 dash, and x3 dash here. Okay, so you understand that along this x1 we'll have the unit vector e1, along this x2 we'll have e2, and along this x3 we'll have e3. For keeping this picture relatively clutter free, I am not explicitly denoting those unit vectors. In a similar fashion, so this is x1 dash, so along this x1 dash we'll have a unit vector e1 dash, along this x2 dash there will be a e2 dash, and along this x3 dash there will be a e3 dash. So what we want to say first of all is that let the angle between this x1 dash axis and this x1 axis be denoted by some angle, and let the cosine of that angle be given by uh, the expression q11. So what we are saying is the cosine uh, of the angle between x1 dash and x1, let that be represented by q11. At the same time, you note that the angle that x1 will make with x1 dash, that will be the same angle, and the cosine of that will again be q11. Okay. In a similar fashion, the cosine of the angle that the x1 dash axis makes with the x2 axis. Okay, so suppose this angle, the cosine of that will be represented by x1 dash comma cos of x1 dash comma x2, that will be q12. Similarly, we can have the cosine that of the angle that, let us say, the x2 dash axis makes with the x3, that will be q23. And so the angle that the the cosine of the angle that the x3 axis makes with the x2 dash will also be q23. Okay, now how can these be utilized in writing the or in making or establishing the connection between these two coordinate axes? So what we'll note is, first of all, the E1 hat dash. So the unit vector along this, lying along this x1 dash axis, what will be that? So the magnitude of that is 1. So the component of that unit vector, the E1 dash unit vector along the x1, the component of this unit vector along the x1, mind you, this is very important, that component will be what? That will just be the cosine of this angle, and that we have already seen is nothing but q11. So this will be q11 E1 hat. In a similar fashion, the angle or the component of this E1 hat along the x2, that will be nothing but q12. And in a similar fashion, the component of the E1 dash along E3 will be q13. So we have this relation. In a similar fashion, the E2 hat dash, that will be q21 E1 hat plus q22 E2 hat plus q23 E3 hat, and finally the E3 hat dash, that will be q31 E1 hat plus q32 E2 hat plus q33 E3 hat. Okay, now we can represent these three relations, these three different relations uh, using the matrix representation. So this can be written as E1 hat, E2 hat, E1 hat dash, E2 hat dash, and E3 hat dash in the form of a column matrix, and this can be written as q11, q12, q13, q21, q22, q23, q31, q32, q33. Multiplied with E1 hat, E2 hat, E3 hat. And finally, this particular matrix representation, that can be represented in short as, in the index notation, as E1 hat dash is equal to, so perhaps instead of calling it the index notation, it would be better to call it the shortened component wise notation, because ideally in the pure index notation we would not be writing these unit vectors themselves. So with that understanding, we write this. So you see, and please make sure that that you verify that this is indeed the correct form from this. Okay, and this has direct connection with what we had written in our previous parts of the lecture. Okay, so we have this connection between the unit vectors in the x1 dash, x2 dash, x3 axis with those in the x1, x2, x3 axis. Now what about the reverse relation? So what I mean to say is that here I have written down three relations where on the left hand side I have the unit vectors E1 hat dash, E2 hat dash, and E3 hat dash. But suppose I want to take the component of the E1 lying along the x1 along the x1 dash. So what will be that? That will be nothing but q11. Similarly, if I take the component of the E1 along the x2 dash, what will be that? So this time you have to be a little bit careful and note that going by our previous convention, The q12 is the angle between the x1, is the cosine of the angle between x1 dash and x2. But here we are not talking about that angle. We are talking about the angle that the x1 makes with x2 dash, or conversely the angle that x2 dash makes with x1. So if we go back to this convention of writing the q's, then the appropriate term that we are looking for is not the q12 when we are talking about this particular angle between the x1 and the x2 dash, rather it is the q21. And finally, when we want to take the component of the x1 along the x3 dash, it is actually the q31 which we need. So with this understanding, let us proceed and write down in a similar fashion as these the E1, E2 and E3 in terms of the E1 dash, E2 dash and the E3 dash, and that we'll do in the next page. So we have E1 hat is equal to Q11 multiplied with E1 hat dash plus, very importantly, it is the Q21 which is present here multiplied with the E2 hat dash and the Q31 E3 hat dash. Next, E2 hat will be equal to, this time we have the Q12 because this represents the cosine of the angle that the x1 dash axis makes with the x2 axis, okay, or conversely that the x2 axis makes with the x1 dash axis. So this is the right term here. For this one, it's very easy. This is the Q22 and this one should be the Q32 E3 dash. And finally for the E3, what we have is Q13 E1 hat dash plus Q23 E2 hat dash plus Q33 E3 hat dash. Okay, and again these can be these relations, they can be together written as E1 hat in matrix representation as just as before. This entire matrix multiplied with the E1 hat dash, the E2 hat dash, let me write that properly, E1 hat dash, E2 hat dash, E3 hat dash, and this entire relation is written as EI hat is equal to Q Ji Ej hat dash. So you please compare very quickly what we had written in the previous page here. It was Ei dash is equal to Qij Ej hat, and here we have the Ei hat is equal to Qji. Instead of the Qij we have the Qji here because the way that these angles have appeared here, and we have Ej hat dash here. So now what we are going to do is and before saying anything else, let me point out that when we are writing these matrix representations, or equivalently the index notation, and particularly the matrix representation, so if you compare this one and this one, okay, so you should not have any impression that somehow we are obtaining this directly by some kind of inverse transformation. Okay, so what I mean to say is that this is a matrix equation, and you can invert these equations to obtain the E1, E2, E3 in terms of this E1 hat dash, E2 hat dash, and E3 hat dash. But in this particular case, we are not doing that. We are purely following the geometrical arguments to set up these axes, and uh, they are as they are appearing. Okay, so we are not doing any algebraic manipulations here to obtain this particular form. These are purely following from the geometrical considerations. Now, what we are going to do next is uh, to uh, to write some general vectors uh, using these relations, and through that process we'll be able to make the connection between how the same vector can be represented in the two different coordinate systems that we have been considering, uh, and through those steps that connection will be clear. Okay, so what we are going to do first of all is, okay, let's go to the next page and let us write down the vector we are interested in. So let this be the v vector, and we have already seen that this can be written as vi ei hat. We have already seen that on the first page of mathematical preliminaries. So this is vi ei hat, and that is equivalent to, in the other coordinate system, vi dash ei hat dash. Now you note that this ultimately represents some sort of a summation. Okay, so borrowing the ideas from the pure index notation and noting that we are not actually using the pure index notation, we can write this thing for our convenience as vj dash ej hat dash. There is no harm in doing that. Okay, there is no harm in doing that. Rather, you'll see that the steps that we are going to follow after this will become quite neat and clean because of writing like this. So what we are going to do here is uh, so we note from the previous uh, page that ei dash is equal to qij ej hat. Okay, so let me write down that in the side here. We have already seen that ei hat dash is equal to qij ej hat. Now you see on the right hand side, this j is a repeated index. Okay, the order of the tensor here is represented by this free index I. On the left hand side also I. Now suppose I want to write ej dash. What can I do? Just like when I was appearing here, the I was appearing in the first index of q, so also I can write like this, qj, and I can write it like some p ep hat. But this is just a dummy index. This p is just a dummy index. I can replace it by k, I can replace it by m, and if I can do those things, I might as well replace this by I. There is no harm here. So if I do that, then qj I ei is a form which will actually help me in achieving my objective here of making the connection between the two different representations in the two coordinate axes. So what is that? So let's consider the fact that vi ei hat is equal to vj dash ej hat dash. Now this ej hat dash, I will use this particular expression. The vj dash remains as it is, and for the ej hat dash I will write it as qj I ei hat. Okay, now you see on the left hand side I have a ei hat, on the right hand side I have a ei hat. So can I not write it like this? that Vi is equal to Vj dash Qji, or equivalently I can write it as Vi, just to make it look a little bit cleaner, I put the Qji first, Vj dash. Okay, so with this step I have obtained some connection between the Vi and the Vj dash. Now I will consider again this relation, but now in the reverse order. So this time I write it like Vj hat Vj Ej hat dash is equal to Vi Ei. Now you see we have already obtained the expression of Ei in terms of the Ej hat earlier. So if we go back to the previous page, here we already have the expression of Ei hat in terms of the Ej hat dash, and we are directly going to utilize this expression. So the left hand side remains as it is, the Vi remains as it is. We quickly take one more look at the expression of Ei. It is Qji here, so Qji Ej hat dash, and again you see both on the left hand side as well as on the right hand side I have the presence of the Ej hat dash. So what I can write this as is sorry, there should be a this should be a Vj dash. Okay, please note this carefully, there should be a Vj dash. So this is equal to Qji Vi. Okay, now because we have too many i's and j's here, I think it will be useful for our later steps to just write this to replace this dummy index I here in terms of another letter k. Okay, all right, now what can we do? You see, we have obtained the Vi in terms of the Vj dash, and reversely we have obtained the Vj dash in terms of the Vi. Okay, now what if we combine these two? Okay, so what we are going to do next is to consider this relation again. So we write this again, and let me separate this part out that there is no confusion. So I write this again as Vi is equal to, I just repeat it, Qji Vj dash, and here I utilize this particular expression here. Okay, so what I obtain is Qji, so the Vj dash will become Qjk Vk. Now in the next step, what we can do is, we see that on the left hand side we have a Vi, and on the right hand side we have a Vk. So if we want, we can get rid of this Vi or the Vk by writing on the left hand side Vk delta Ik. So this should give me Qji. So these Q's remain the same as in the previous step. The Vk also remains the same, so the entire right hand side is the same as before, but on the left hand side, through this substitution power of the Kronecker delta applied in reverse this time. So here we have Vi, we have applied the substitution power in reverse now. So we have the emergence of this Vk, which is also present on the right hand side. That was the motivation. So ultimately what we can do is we can write this as Qji Qjk is equal to delta Ik. Now before going forward with any further step, whenever you do these kinds of tensor algebra, you must always make sure that whatever you are obtaining as a final step, there the order of the tensors as represented by the free indices, as well as the those free indices are, they are consistent on the left hand side and the right hand side. So on the left hand side we have j as the dummy index, so that does not matter, that is not contributing to the order of the tensor. The order of the tensor of whatever this entity is there on the left hand side, that is contributed by this I and this k. So there are two free indices, they are I and k. So on the left hand side we have a tensor of order 2, and on the right hand side very consistently we have again the presence of this I and the k as they are on the left hand side, and this again is a tensor of order 2. Say, so everything is nice. Now you can check that this qji, qjk, that can be written in the compact notation as q transpose contracted with q itself, and this Kronecker delta is nothing but the compact notation for the identity matrix. Okay, so this I is nothing but, so I can just write down here in the rough very quickly. So if you want to write down the matrix representation of this I, it is simply the very familiar 1 0 0 0 1 0 0 0 1 matrix, the identity matrix. Okay, so the I second order tensor is nothing but the compact notation for this identity matrix, and this here is a very important relation. So you see, we have not only connected the vector representation. So let me go back to this figure. We have not only managed to connect the vector representation in these two coordinate axes, but in the process we have also managed to find out that the transformation matrix q. Okay, so this q is the second order tensor by itself, and in the matrix representation it is referred to as the transformation matrix. So very explicitly speaking, this is our transformation matrix here, this entire thing, this 3 by 3 matrix. So that transformation matrix is orthogonal. Okay, so that's a very important fact. So with this we are going to conclude this part of the lecture, and in the subsequent lecture we are going to finish up this chapter on mathematical preliminaries with one small but with one very important topic of discussion, which will be again important for what we discuss in the subsequent chapters. All right, thank you very much.